The reinforcement learning approach then will use this value function, so we can construct a lookup table with all the possible states of the game, all the possible situations that our player can encounter, and each of these states will have a value assigned, which in this case is a number that could be 0, 1 or 0.5. 1 is a value of the value when the player, the reinforcement learning player, has won, 0 when it has lost, or 0.5 where it is yet impossible to know if the agent will win or lose. So the algorithm will be updating these values, that initially all of them can have 0.5 because we don't have information about the different states, and the algorithm is going to update these values until we have found the right value function, the right values, and the policy will be derived from this value function. So we need to define this table with the value with the values of the states, and then the approach, the reinforcement learning approach, is that the player, the agent, will play a lot of games against the opponent, and at each moment, given the current state, the agent will select one of the possible actions available in that state. Sometimes it will perform the optimal action, which is marked here with this star, and sometimes the agent will perform some suboptimal action. We will consider an exploratory move when the agent decides to perform a suboptimal action, and we will consider a exploitation move when the agent decides to perform the optimal action given the current state. When we talk about optimal and suboptimal actions, we are considering that at each moment in the learning episode, the agent will be able to estimate what is optimal and what is suboptimal, but given the current information that the agent has at that moment. So initially, what we're saying here is that initially the agent, even when the agent selects what it considers to be the optimal action, the truth is that initially the agent doesn't have enough information to really select what is optimal. So what we say here, selecting the optimal, means that agent will select the action that will lead to the state with largest value as estimated at that moment. Okay, so sometimes it will perform a greedy move according to its current estimation of the value function, and sometimes it will perform some exploratory movement. So for example, it could perform exploration 10% of the time. So during the game we start in some starting position, some start state A. Here the opponent makes a move, and we transition to some state B. In state B, on this state, the agent decides to execute what it thinks it's the optimal action at that moment, C star. Then an agent decides its action, D, and maybe at some point the agent decides to do an exploratory move. So instead of deciding the best, the star action, the optimal action, decides for a random action just to explore what happens with that action. Then the agent will move again, and so on. So every time we run and sequences of actions from some starting position until some end position, we are running what we call a training episode. In reinforcement learning, we talk about training episodes, and we need many of them. Usually we need thousands of training episodes until the agent can have a good estimation of the value function and the policy function for this specific problem. So here we talk usually about the state S and some next state, which is written as S prime, the next state. And we apply learning rules that look like this one. So the value of some state will be updated with the current value of that state plus some portion, some alpha, which could be called the step size, the learning step size, alpha. And here we have the subtraction of the value of the next state that we transition to after executing an action, and the value of the previous state where the agent was before executing the action. This is a learning rule that we call temporal difference, because we are considering that the difference between a time when the agent was in state S and the value of the state in the next time step, once the agent has transitioned from state S to state S prime. So the learning rules that we will see in reinforcement learning look very similar to this one. In reference to this alpha parameter, that is a value between 0 and 1, this is step size parameter, or learning rate. If for this specific example of tic-tac-toe, if the agent plays against one opponent, if we reduce the size of alpha as the interactions or training episodes go, and until we make alpha equals 0, decreasing alpha gradually, the algorithms following this kind of rule can actually converge and learn the optimal policy for that opponent. Okay, but if you want to train your agent against several opponents, assuming that each of the opponents will have a different policy of behavior, a different strategy to play, then what we need to do is to keep alpha constant. This will allow the agent to adapt and learn different strategies according to the different opponents that it will play against. We will talk more about this alpha and the importance of the values that we give to this alpha later. When we implement reinforcement learning with state spaces that are finite and possibly small spaces. So when the environment has a small number of states, we can implement these algorithms using a lookup table. Okay, so we can store in our memory of the program an array that will store the value of each of the states. However, when we want to apply this to problems in which we have an infinite number of states, or simply a very large number of states, then we cannot use a lookup table. So we need to implement a function approximator. And one way to do that is to use a neural network. So this way, even if we have an infinite number of states, we don't have to gather information about each of the states, because it is impossible. But we can approximate. Maybe we have information about a specific state that we happen to visit many times, and that information about that specific state can be used to approximate the value of some states that are in the neighborhood of that specific state, and that can be achieved using a function approximator. So this tic-tac-toe problem that we have talked about is a simple problem, and this is just an example that is useful to try to explain the approach behind reinforcement learning. It doesn't mean that reinforcement learning can be applied only to these simple problems. Many problems that are solved using reinforcement learning are much more difficult than this tic-tac-toe. This tic-tac-toe is easy because it is a finite number of states. Usually you apply this to an infinite number of states. In this case, a specific case of tic-tac-toe, you can look ahead one step. So you can, given the current state, you can let's say visualize what could be the next possible states. There are not too many, but there are problems in which you cannot. For example, if you are training a system, humanoid robot, you want the humanoid robot to learn to walk, then it's impossible to know the position of the robot in the next time step, all the possible positions. It is simply too complicated considering all the variables of the environment. Also, in the case of the state, here in tic-tac-toe, you can completely observe the state. In real world applications, you don't know, or you cannot observe the complete state of the environment. Like, for example, if you want to control a drone, it is impossible to know sometimes, to observe completely the space surrounding the drone. So even though we have talked about this easy problem, reinforcement learning algorithms can be applied to solve much more challenging problems. So there are some important or notable applications of reinforcement learning in the past. Like, one of the main applications is the TD Gammon, implemented by Thesauro. This system learns to play backgammon at in a very high level of performance. I will talk a bit about that in the next slide. Also, these algorithms have been applied for elevator control. In this work, a system of 4 elevators was trained using reinforcement learning to optimize, or to, in this case, to reduce the time people needed to wait for the elevator. And there are other applications, like for inventory management, and another one for dynamic channel assignment in the case of radio channels for telephone networks. In the case of the T-Gammon, it has been a very important application of this, because it was a very complicated game to dominate, to control. So in this approach of T-Gammon, the researchers applied a neural network that was used as a function approximator of the value function, and this system learned playing very many games against itself and applying a temporal difference rule to estimate the value of each of these states. In this kind of game, there is a lot of states. It is not an infinite number of states, but it's a very large state space. So that's why they needed to approximate the value function. In these large state spaces, you can only visit a very small set of, or a very small subset of states. So you need to use some approximator, some way to generalize the knowledge you have learned. And well, this work was published first in 1992, so it's a 30 years old work. The other system that is good to consider is the elevator dispatching system. This system was trained with a building of 10 floors and 4 elevator cars. In this system, the states of the environment were coded as or containing as a vector containing the bottom states, the positions of the elevator cars, the directions in which each of the cars were heading to at each state, and the motion states of the cars. Also, if there were passengers in the cars, and if there were passengers in the halls waiting for the elevator. So all these variables were considered to represent the states of the system. In terms of the actions could be stop at some floor, or simply go by some floor, or go to the next floor. These kind of actions were considered in this learning system. And the rewards, or the reward function, was roughly -1 per time step for each person waiting. So given 2 possible solutions, the system was given a reward that was simply a -1 per each person that was waiting per each time step. So in this system we are talking about 10 to the 22 states. So even though it could look simple, we're talking about a problem with a very large state space. More recently, the company DeepMind, which was acquired by Google in 2015, designed a reinforcement learning algorithm that was able to play against humans, or compared to humans, with a comparable performance of a human, or many of the games that it learned to play. We're talking about Atari games, 49 Atari games. Many of these games, the system learned and got a higher performance than the human level, than a human expert in these games. So this system was very important because it motivated the people involved in reinforcement learning research. And the importance of this algorithm is that the system that is called DeepQ network is that this network learns from the pixels in the screen of each of the frames of the game, learns what is the best action you should perform with the control. Okay, maybe going up, diagonal, or right, or if you need to push the button or not. And the same architecture learns 49 different games of this Atari console. It uses layers of convolutional networks and layers of fully connected neurons in this deep network. So this work was so important that it was even published in Nature magazine. So here is the link to the project. You can read more about that in this link. And after that, DeepMind designed AlphaGo 0, which is we could say the state-of-the-art algorithm in reinforcement learning. It also uses a neural network to store the value function of the system. This project was published in 2017, and the importance of this system is that this system plays the game called Go, which is more complicated even than chess, and it defeated the world championship of this game. And the system is very similar to Didigamo in the sense that it learns by playing against itself. It needs around 3 days to learn a policy that is comparable to championship players. They say that in the first third of the learning process, the system learned to play like a normal person. In the second term of the learning process, it learns to play like a champion. And if you let the system you let the system keep learning more days, this system managed to discover strategies that are completely new to this game. It found strategies that have not been registered in the history of this game. So it's a very powerful system. The key breakthrough in this system is that it combines a neural network and a system to do some smart search of the state space, so it optimizes the training time. Remember that in these games we have too many states. We cannot visit all of the states, so we need a way to reduce the number of states that are more promising to visit, and this system does exactly that. It combines the powerful of the deep neural networks to store a very complex value function with a very smart search strategy to reduce the search space. So this has been an introduction, a very fast introduction to the field of the new reinforcement learning methods. In the next presentation we will talk about the bandit problem. And the bandit problem is a very foundational problem that we need to study in order to understand the inner workings of the reinforcement learning methods. So that's what we are going to do next.